Hi, everybody. We're doing section 2.4, the derivative. And this is like the big thing of calculus, a huge thing in calculus, the derivative. And the best way I could describe a derivative is if you're driving, let's say you want to know how fast you're driving. So if you're, if you drive 50 miles and it takes you an hour, so you drove 50 miles an hour. The thing is that you might have gone slower points, faster points. You're not a machine. You're driving a machine. But I'm just saying, you may have gone a little bit faster here, a little bit slower there. If you want to know your speed at one instant, 1 second, what is my speed right now? Because I don't know if it's 50, it might be 52, it might be 48, it could be whatever. So that speed at that instant moment, that would be someone would use a derivative for. And that's a little harder to figure out just with algebra, because algebra, I can say, hey, I drove 50 miles, it took an hour, 50 divided by an hour, whatever, it's a simple distance equals rate times time. So just, so rate is equal to time divided by distance divided by time and pal. So, if I drove 100 miles and it took 2 hours, 100 divided by 2 is 50, so it's 50 miles an hour. That's for the whole trip. But if you want to pinpoint it to one precise second, so to do that with algebra is a little bit harder, or I shouldn't say harder. It's it's pretty really, there's really no algebra way to do it, and that's really where calculus now comes into play. In other words, if students say, what's the difference between, actually we had this already in previous sections, but what's the difference between calculus and algebra? It's kind of the same thing. And the difference is the idea of a limit. And we're going to use the idea of limits to solve this problem. Like, how do I figure out how I'm going with this, how fast I'm going with this precise moment? Okay, so that's what we're saying. Another function, another curve, another thing we could do with derivatives, if you have a curve and you want to find, if you have a straight line, you want to know the slope of the line, well, that's easy. You just, change in y divided by change in x, blah, blah, blah. There's formulas for that. Everything's cool. But what if you're at a certain point on a curve? You want to know, if I would draw a tangent line to that curve, what would be the slope of that tangent line? Well, that's also something with algebra. Good luck trying to do that with algebra. With calculus, we're going to learn how to do it. And again, it's also going to involve limits. That's just my little preamble for section 2.4. Okay, rate of change. Let's take a look down here. Rate of change. So let's look at the definition of the average rate of change. So the average rate of change, so y is equal to some function, y equals f of x. The average rate of change, now I'm going from x equals a to x equals a plus h. So a is 1 point, so like a could be 5, h could be 2, so I'm going from 5 to 7. I'm going from mile marker 5 to mile marker 7. And you want to know, we want to figure out the rate. Well, if I take f of a plus h minus f of a, that's really how far you went in that time, because you started out at f of a, and then you ended up at f of a plus h. So this top thing here is really kind of distance, and the distance that the y value changed. And here you started at point A on the x, in the x direction. You started at point A and you ended up at point A plus h. So a plus h minus a, that's the distance you travel in the x direction. The top is the distance you travel in the y direction. And that really is change in y divided by change in x. That's rise over run. That's the classic, and so now all we do here, we just cancel out the a's, because you have a minus a. So you have f of a plus h minus f of a over h. And of course, h won't be 0. Well, if h is 0, there's really nothing to talk about, because you didn't go anywhere. We want to know, you went from a to a plus h. That's like saying you went and you just stopped. You didn't go anywhere. So there's nothing to talk about there. Alrighty, let's get into some. Let's look at an example. Okay, we're gonna go to business. So the revenue, what is revenue? Revenue means how much money you take in. It's what's in between revenue and profit. Profit means you look at the revenue, how much money you take in, minus all the expenses that it costs you. So, for example, if I'm running a movie theater, if I count how much money I made from all these tickets, I sold all, whatever 1,000 tickets, wound up being whatever it was. I don't know how much. I didn't even know how much a ticket cost. I didn't even know what a ticket costs a movie these days. But when I was a kid, it was a little cheaper, So I sold this many tickets. It cost this much per ticket. That's my revenue. But I had to pay for electricity. Had to pay for the maintenance. Had to pay to buy them. I have to buy the movie from a producer or whatever. There's a lot of expenses. So if you take the revenue minus the expenses, that's what we call profit. So revenue in dollars from the sale of X plastic planter boxes. Try to say that 3 times fast. Is given by this function, R of X. That means the revenue function of X is equal to 20X minus 0.02X squared. So, see, X is how many boxes I sold. So I have a formula involving X because my revenue if I sell one plastic planter box versus my revenue if I sell 10 versus my revenue if I sell 100, these are different amounts. So that's why we have a whole formula here involving X. And X goes between 0 and 1,000. I guess 1,000 is all we got. I don't know why it's limited by 1,000. Maybe that's the most you could sell. I have no idea. So what is now? So this function, this graph here we have on the side, this is that function. So my revenue, from the sale is given by this. That's my revenue. And what is the change in revenue if production is changed from 100 planters to 400 planters? I'm selling 100. That's 100 right here, and here I'm selling 400. So what is the change in revenue? The change in revenue is I'm going from 1,800 up to 4,800. So from 1,800 up to 4,800, that's 3,000. So if I'm selling 100 planters and now I increase it to selling 300 more planters, I increase it to 400, which is 300 more. I wind up taking in $3,000 more dollars. I wind up taking in $3,000 more dollars already. And let's look at question B. What is the average rate of change in revenue for this change in production? The average. So the average is going to be the difference in price divided by the price. Average is on a price per unit. It's on a price per unit. So the difference in price is R of 400 minus R of 100. And we said that was 3,000. Divided by the number of additional units I made, which is 400 minus 100, which is 300. So 3,000 divided by 300 is $10. So the average rate of change in revenue is $10. So the average rate of change in revenue is $10 per planter when production is increased from 100 to 400. So we're not saying that you charge $10 more for each planter. We're not saying that, but it's $10 per plant. It's $10 per planter. In other words, if you take the entire revenue change and divide that by how many planters you have, it comes out to be $10. Per plant. That's what we would say per planter. Okay, let's look at the second example. This is the leaning. I'm going to go out on a limb here and say this is the leaning tower of pizza. A small steel ball dropped from a tower will fall a distance of y feet in x seconds. And explosive will drop. As given approximately by the formula, y equals f of x equals 16x squared. Meaning that if x is the number of seconds and y is the distance, y is how much it drops, the distance that it goes. So So for 1 second, this is going to be 16 feet. If it's for 2 seconds, it's going to wind up being 16 times 4, 64 feet. If it's 3 seconds, it winds up being 16 times 9, which is 225 feet. Oh, it has all the numbers right here. 144 feet. Oh, actually, it goes right here. So this is the start thing. After 1 second, you've gone 16 feet. After 2 seconds, you've gone 64 feet. After 4 seconds, 3 seconds, you've gone 144 feet. Notice that you're going faster and faster, because obviously, it took you 1 second to get from 0 to 16. Now 1 more second. So if it takes 1 second to go from 0 to 16, you think the next second would get me to 32, another 16 feet, but it doesn't just get you to 32, it gets you to 64. And then the next second gets all the way to 144. So notice it's changed, which means it's going faster and faster. And the fancy word for that is called acceleration. It's accelerating. So here's let's take a look here. All right, so we want to find the average velocity from x equals 2 to x equals 3. So in between 2 and 3, what's the average velocity? Well, again, it's going to be distance divided by time. So the distance is going to be, where am I? What? They just changed the problem here. Cool. But it doesn't make sense. Is it a new? It was a new. Did they just change? Oh, no. That's example 2, right? 132. Oh, we're not talking about driving to San Francisco. We're talking about. Okay, so the average rate in that second going from 2 to 3, it's going to be 144 minus 64 divided by 3 minus 2, which is 1. So it winds up being 80 divided by 1, which is 80 feet per second. So the average rate, now that doesn't tell you what your rate is at 2.74 seconds, but the overall for that entire second, which I guess 1 second could be a very long amount of time. Especially if you're getting drilled, if your teeth are getting drilled by a dentist, it's 1 second can be a very long amount of time. So, okay, that's A. Now for B, find and simplify the average velocity from x equals 2 to x equals 2 plus h. So we want to find it, we want to simplify it. So x equals, so we start with 2, we go to 2 plus h. So if I take 2 plus h and I square it, you're just doing a regular foiling it out, whatever. And then I multiply everything by 16, I get 64 plus 64h plus 16h squared. Because I just squared this thing, multiplied everything by 16. And then I'm subtracting the 64. So notice 64 minus 64, it all cancels. Once I do that, I have 64h plus 64h squared. I can factor out an h. And notice that the factored out h cancels with the h down there. So my average velocity is going to be 64 plus 16h. 64 plus 16h. Now, if you remember, now in our problem, we started out when f is equal to 2, and we went 1 second. So from 2 to 3, that's 1 second. So it'll be 64 plus 16 times 1, which is 64 plus 16, which is 80. So our example of 80 would be like a special, our case, A would be like a special case of B, I guess that's the best way I can say it. Find the limit of the expression in part B as h goes to 0, if that limit exists. Well, that's going to be an easy limit to find. I just have to take 64 plus 16h, send h to 0, which basically what's going to happen is that the whole the whole 16h is going to, as my math teacher used to say, it's going to go on vacation. It's going to disappear, and I'm left with 64 feet per second. So the limit of this is 64 feet per second. So let's move on. And D, discuss the possible interpretations of the limit from part C. Okay, fair enough. Let's discuss it. Well, the average velocity over smaller and smaller time intervals approaches 64 feet per second. This limit can be interpreted as the velocity of the ball at the instant of 2 seconds, that the ball has been falling for exactly 2 seconds. Therefore, 64 feet per second is referred to as the instantaneous velocity at x equals 2. So if there was like a cop with a radar gun and he shot the ball right exactly at 2 seconds, it would be going 64 feet per second. I don't know why I have to bring in such unfun thoughts. Anyway, so here's the formula for instantaneous rate of change. So y equals f of x, that's the function for my position. That's my position function, I call it. And so the instantaneous rate of change at x equals a is a limit as h goes to 0 of f of a plus h. So whatever the function is, in our previous example, it was 16x squared. So it'll be 16a plus h parentheses squared. But whatever the function happens to be, and we had a previous problem with a different function, whatever the problem is, and then minus f of a. And of course, if the limit exists, obviously, if the limit doesn't exist, it's not what I'm talking about. Now, the adjective instantaneous is often omitted with the understanding that the phrase rate of change always refers to instantaneous rate of change and not the average rate of change. Similarly, velocity always refers to the instantaneous rate of change of distance with respect to time. So that's a good thing to know. Okay, now let's talk about slopes of tangents, because why would you want to have a tangent without a slope? Okay, everybody, now we're going to talk about figuring out the slope of a tangent line. Again, if I have just a straight line, then that's easy finding the slope, because I just do I do the old formula, y2 minus y1 over x2 minus x1. You know that formula. I'll show you all. I see it's here on the bottom left of the page. You know, it's a famous formula, and you just do that, pow. But we're not talking about a straight line. We're talking about a curve, and we want to find what would be what would be the slope of the tangent line, the line that's tangent to the curve. Now, once I know, if I knew 2 points on the line, I could figure out the slope. I don't know 2 points. I just know it goes. I just know it hits this curve at a certain spot, and it's tangent to it, so it has to be in a certain position. But what's going on over here? So, what we're going to do is, the strategy is we're going to look at a secant line. So here's the point P. P is the point of tangency. So what we're going to do, instead of looking at the red line R to try to figure out the slope, we're going to look at the green line here, which is a secant line because it hits it in 2 places. And we're going to take the limit as Q gets closer and closer to P. That's kind of what we're going to do. So we're going to look at a line that's not the tangent line, but close to the tangent. And then we're going to look at the limit when those 2 lines kind of converge. And that's how we're going to use limits to solve this problem. That's kind of the basic strategy. So again, there's a secant line. Now, this point here by point P, that's A comma F of A. This point Q is A plus H comma F of A plus H. And so here's our, so y2 minus y1 over x2 minus x1 is f of a plus h minus f of a over a plus h minus a, which is f of a plus h minus f of a over h. Notice that's the same thing we got. That's similar to what we got when we did, rate of change and instantaneous rate of change, velocity and that kind of stuff. So that's kind of cool. Oops, I went too far. We're over here. So for secant line, so let's say we have a parabola, y equals x squared. And here is a nice little parabola. And we want to find the slope of the secant line from a equals 1 to h equals 2 and 1, respectively. So if a equals 1 and h equals 2, so I'm going to plug, so it'll be 1 comma f of 1, and that comes up to be 1, 1. And then 3 comma f of 3. F of 3 winds up being 9 because the function just squares. So 1 squared is 1, and 3 squared is 9. That was easy enough. And so I have f of 1 plus 2 minus f of 1 over 2 because x has traveled 2 units. So it's 8 units divided by 2 units, which is 4. And that's the slope of that secant line. Let's look at it. Let's make h smaller. again, because we want to shrink h to get it smaller and smaller. We want to get h as close as we can to 0. So let's make h smaller. So we have, again, it's 1 f of 1 is 1, 1. And then you have 2 comma f of 2, which is 2, 4. Notice that here was 3 f of 3. Here it's 2 f of 2 because this was going a distance of 2 units. That's only a distance of 1 unit. Anyway, in the x direction. And f of 1 plus 1 minus f of 1 is 2 squared minus 1 squared, which is 3 divided by 1. So it's 3 divided by 1 is 3. So the slope. So in one case, the slope of the tangent is 4. When I make the tangent closer, the first secant, where the secant, the 2 points of intersection were a little bit further apart, the slope was 4. And now with the two tangent, they get close together, the slope becomes 3. That doesn't mean that always when they come closer to closer, it's going to decrease. It just happens to be in this case. And now what was B? Find and simplify the slope of the secant line for a equals 1 and h is any non-zero number. So what I'm going to do is I'm going to take f of 1 plus h minus f of 1, which means I'm going to square 1 plus h, and I'm going to square 1. So it's by the just foiling it out, you get 1 plus 2h plus h squared when I foil this guy out, minus 1. The ones cancel. Notice how convenient it was that the ones, remember before we had the 64s canceled, and now the ones cancel. That's actually going to happen like all the time, pretty much, for these kind of like polynomial thingy things. And I factor out an h, then I cancel out the h, and I have 2 plus h. This we're going to see is going to happen a lot, especially when we do like polynomials like we're doing now. I'm not saying it's going to happen for every function in the world always, but it's going to happen a lot, especially for polynomials. So factor out the h, I have 2 plus h, how? Which means when h goes to 0, so if h goes to 0, that means the secant hits the parabola very close to it, to itself. So when h becomes 0, it would, and I can't just set h equal to 0 because I have 0 on the bottom of the fraction. But as h gets closer and closer to 0, the slope gets closer and closer to 2, which means it's basically going to have a slope of 2. And we're going to see that. We're going to show you. We're going to see that on. And that's really what. That's probably what D. So C, find the limit, and then D, discuss the interpretation of it. So the limit is going to be 2, of course, because the h just goes on vacation. I'm left with the 2, and D, the interpretation is that will be the slope of the tangent, because as the secants get closer and closer to the tangent, the secants kind of become as the point of intersections of the secants get closer and closer, it kind of becomes like the tangent line. Now let's just, for illustration, let's go. So this is y equals x squared, and we're looking at the point when x equals 1. So let's go back out here. Let's go to Desmos. Okay, so we have y equals x squared. And now I want to do y equals, I'm going to do this, y equals 2x minus, y equals 2x. Let's do that one. So y equals 2x. So this has a slope of 2, but if you notice, it's not, it's not at the, it's not tangent. So let's say I make it minus 1. Let's see if that does anything. Let's play around with this a little bit. Now, look at that. There you go. I got on my first shot. I was gonna try to I thought I would overestimate it. See, if I had done minus 2, then it would have had me down there. But when you do minus 1, it just hits it right. If you notice, see, there's a dot there. That's the, it always, Desmos always tells you the x-intercept and the y-intercept, and it tells you when 2 curves intercept. But notice that there's only one place where those 2 curves intercept. So the equation of the tangent is y equals 2x minus 1. And you can see the slope of that tangent is 2, which is what we're saying here. And I would figure that out with calculus. Now, how would I figure out? I kind of guessed with Desmos what the equation of the tangent is. How would you actually figure it out? Well, that you can do with algebra with the point slope formula or something like that. And we will have and we will do problems with it. But I just want to give you a little, little heads up. Okay, back to the salt mines. So the definition of the slope of a graph and a tangent line. So it's the limit is h goes to 0 of f of a plus h minus f of a over h. And we're getting so close to something called the derivative. In fact, it's going to start right down here, derivative. So the basically to make a long story short, if instead of having a, I want a formula that's going to work for any a, for any x value. So I just do, well, let's just cut to the chase. I don't want to. I think if I over-explain it, it's going to make it worse. So we want, so f prime is the symbol we use for derivative. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. So it's basically the same formula we had just on the page before, only instead of a plus h and f of a, it's f of x plus h minus f of, so I don't have to only do this for a, because we were just talking before when a equals 1, or I don't have to do a separate problem when a equals 1, a separate problem when a equals 2. This way, whatever the x is, then we're good to go. And this is called the derivative. And derivative is a huge thing. And the way we say this, we say f. So this we say f of x. I mean, you had that little symbol there. I don't know, it looks like kind of an apostrophe. You say f prime of x. So if I say f prime of x, that means the derivative of the function f, of course, with respect to x. So if f prime of x exists for each x in an open interval, then we say that the function f is a differentiable function. It's differentiable over the interval a comma b. And that is the story. By the way, so now you're ready, finally, for your first calculus joke. What is the derivative of a clock? Prime time, get it? Because prime. Anyway, so that is the story. Okay, moving on. This is just a summary. So you can get velocity, instantaneous rate of change. So these are all the different uses we have for okay. F of x is equal to 4x minus x squared. Find f prime of x using a 4-step process. Now, I don't know if it helps or makes it some. Now I'm just talking for myself. This 4-step process, I don't know if that makes it better or worse. Sometimes when you explain things very thoroughly, it makes it harder to understand because it gets more awkward and bulky and more confusing. It's like, you ever see when someone gives you directions to go somewhere and the directions like overly, they're overly, sometimes I find like Google Maps, it'll give directions and the directions have 5,000 steps, which is just telling me to go from this street to that street. But but technically, whatever. Go on the right, go on the on-ramp, go on the off-ramp. Yeah, they give me like, whatever. Anyway, that's just me. So anyway, moving on. The reason I'm bringing that example is because I used Google Maps recently and I wound up getting like lost, not totally lost. I got lost for a few minutes because they gave more directions than necessary and I wound up turning someplace I wasn't supposed to turn or turn the whatever. Anyway, or not turning, it was very confusing. Anyway, so we want to find f of x plus h. We're going to need that first because ultimately we want f of x plus h minus f of x. So we're going to start with f of x plus h. So I take x plus h and I plug it into the x's over here. So whenever I see an x, that x becomes an x plus h. So it's 4 times x plus h minus x plus h squared. And that's going to be 4x plus 4h minus x squared minus 2xh minus h squared. That's f of x plus h. Now, if I subtract from this f of x, it winds up being the 4x plus 4h minus x squared minus xh minus h squared, and then minus the 4x minus x squared. But notice that notice what's going to happen is that the 4x and the 4x and the x squared are going to cancel. They have a minus x squared, I have a minus x squared, so those are going to cancel out. I'm going to be left with 4h minus 2xh minus h squared. Notice that each term has an h in it, so I can factor out the h, which I do down here. Then I divide by h and it disappears. And now I'm left with 4 minus 2x minus h. But since the h is going to be going down to 0, it's just going to kind of disappear. My final answer is going to be 4 minus 2x, which is going to be, I guess, step 4. And there we go. So f prime of x is equal to 4 minus 2x. And that is beautiful. Now, so that's a 4-step procedure. Whatever way you want to look at it. I always learned this is how you get a derivative, and never broke it down to steps. Again, some people find breaking into steps makes it easier for them. Some people find breaking the steps makes it harder for them, but whatever floats your boat, as we say, there's an expression like that. Alrighty, let's find the slope of a tangent line. So we had the function 4x minus x squared. And we found the derivative is f prime is 4 minus 2x. So the slope of a tangent line to the graph at any point, f comma f of x on the graph is m equals f prime of x minus the slope is f prime, which is 4 minus 2x. Now we want to find the slope of the graph at x equals 0, and we also want to find it when x equals 2, and also when x equals 3. And then want to graph them using the different results. Well, I just take these 3 values, 0, 2, and 3, plug them into my f prime. So when x equals 0, the slope is going to be 4. When x equals 2, the slope is going to wind up being 0 because it's 4 minus 4. And when x equals 3, the slope is going to wind up being negative 2. And if you look at it, here over here it's 4, over there it's 0, and over there it's negative 2. Notice that it's negative as I'm going up the hill. I'm sorry, it's positive as I'm going up the hill. It's 0 up on top of the hill, which kind of makes sense. And then it's negative as I'm coming down the hill. Now, that was not just a little comment that I made just now. That's going to be extremely important to realize that. When I'm going up the hill, it's a positive slope. When I'm on top of the hill, it's 0 slope. As I'm coming down the other side of the hill, the bottom of the, I'm going down. Now, what do you mean up or down? Why did you say this side is up and that side is down? So we're talking about as we're going towards the positive x direction. So as I'm traveling towards the positive x direction, I'm going up a hill, get to the top of the hill, and go down the hill. So traveling towards this positive x direction, when I'm going up a hill, I'm going to have a positive slope of all the different tangents. When I'm on top of the hill, my tangent is going to have a 0 slope. And when I'm coming down the hill, my tangent is going to have a negative slope. And that is something that we're going to see a lot of. And I'm just sort of foreshadowing, like Dickens used to foreshadow things. Okay, and the next thing we want to do is, discuss your graphs. Okay, so we're done with that problem. Okay, let's look at another example. Now this is going to be a little tricky because this is not a polynomial, but we can still do it. We could definitely still do it because we are super smart. How do I know we're super smart? Because we could leap tall math problems in a single bound. That's how I know. Okay. Find f prime of x, the derivative of f at x for f of x equals 1 over x. So first we find f of x plus h, which is 1 over x plus h. Then we do f of x plus h minus f of x. So I have 1 over x plus h minus 1 over x plus h minus 1 over x, because that's f of x plus h, and that's f of x. But I want to combine these two fractions, a little algebra here. So I want to getting x minus x plus h over x times x plus h. The x's cancel as usual, and I get negative h over x times x plus h. Now, of course, I'm going to divide this by h, which is what's going to happen here, is that this h down there is going to wind up canceling that h up there, and I finally get negative 1 over x times x plus h. Again, a little algebra. But you'll notice that a calculus problem, it's like one step of calculus and like 9 steps of algebra. You know, it's a lot of you know, it's a lot of algebra in every calculus problem. And so finally, the limit is h equals to 0. Well, basically that h just becomes 0, so it just becomes negative 1 over x squared. And that, my friend, is the answer. Negative 1 over x squared. And let's see if we graph that at all. All right, I want to go back to that negative 1. So let's just, we're over here. Okay, 1 over x. So we have, so the answer was 1 over x. I mean, the function was y equals 1 over x. Let me just, right here, let's go to Desmos. Where's Desmos? Right here. Now the derivative, we said, is y equals negative 1 over x squared, which is kind of interesting. And when x equals, I'm sorry, but that's the derivative. See, what's the actual, so let's say x was equal to 1. So if x equals 1, then the slope is going to be negative 1 over 1. So if I do y equals negative x, now negative x should be a slope when x is equal to 1. But when x is equal to the 1, the function is actually up there. So I want to get it from here. So I'm going to add 2 to this. Again, I'm just kind of eyeballing it. And look at that. Pow, a beautiful tangent. Now, if x equals 2, the slope would be negative 1 over x squared, which is negative 1/4. So it'll be negative, and it's there, but I want to get it down there, so I have to subtract 1. And that is the tangent right there when x equals 2. Oops. That's the tangent right there when x equals 2. So it's so I'm at the 0.2 comma 1/2, and the slope is negative 1/4. That's pretty awesome. That is pretty awesome. So we figured that out with calculus. Yay! Okay, let's go back to the yeah. So let's do some more examples here. Okay, for now we have the square root of x plus 2. So let's do f of x plus h. So that's square root of x plus h plus 2. That was simple enough. There's nothing to do now. Now f of x plus h minus f of x, that's the next thing we want to do. So square root of x plus h plus 2 minus square root of x plus 2. Notice that the 2's are going to cancel. So I have square root of x plus h minus square root of x. Yeah. And divide that by, put that in a fraction and divide it by h. So I get this guy right here. Now, I want to work this out. See, in theory, you could stop right at this point. The only thing is, I'm not, you know, I want something where if I would just plug in h equals 0, it's going to have 0 on top, 0 on the bottom. I want to try to work this a little bit with some algebra. So what I'm going to do is I'm going to multiply top and bottom by x square root of x plus h plus square root of x, well, top and bottom. And this is going to create like a difference of 2 squares type situation. So on top, I'm going to have x plus h, plain x plus h minus plain x. Because I multiply the square root times the square root, it just becomes the regular thing. And on the bottom, we're going to have h times this whole mess. And now x minus x cancels. Have h, there's also just an h on top, but that h on top is going to cancel out with this h over here. Not the h inside there, but the h that's over here that's multiplying. And I have 1 over rad x plus h minus x. And then finally, if I take the limit as h goes to 0, I can just plug in 0 for h. You see, you can't see why did I do this whole multiplying thing? Because the easiest way to find the limit when h goes to 0 is just plug in 0. But I couldn't just plug in 0 because I would get 0 on the bottom of a fraction. So I had to do a little algebra magic to get this to simplify this in a way where I wasn't plugging h into the bottom of a fraction, and that's what happened. So I'm plugging 0, I should say. Yeah, I am putting a 0 for h, but overall it's going to be rad x plus rad x, which is actually going to be 1 over 2 rad x. And that's our final answer, 1 over 2 rad x. That, my friends, is the story. And let's celebrate by analyzing some sales. Because people, when they're happy, they go shopping. When they're sad, they go shopping. And then there are crazy people like me who, when they need something, they go shopping. That's pretty much the only time I go shopping. I know people say retail therapy and it makes them feel better and blah, blah, blah. Shopping does not make me feel better, but I go shopping if I need stuff. Anyway, that's just me. That's just me. Everyone's different. All I know is I once had to take my daughters to the mall. I thought I was going to die. I was like getting dizzy. And I went to that place. It was so much pink. It was Claire's. Oh, there was so much pink there. I couldn't handle it. I was getting like dizzy in old days. I don't know. Anyway, a company's, that's just me. A company's total sales in millions of dollars, T months from now are, which means right now is time 0. Now we're at ground 0 for time, of time, starting from now. So going forward, T months from now is going to be in the formula S of T is equal to radical T plus 2. Now, how do they know that? I don't know. Now, how do they figure out this formula? That's a whole field of math, figuring out that formula. And that's a really interesting field, and pays very well, by the way. I'm just saying. So find and interpret S of 25 and S prime of 25. Well, S of 25 is going to simply just stick 25 into the T. So you get square root of 25 is 5 plus 2 is 7. That's just going to be 7. Use these results to estimate the total sales after 26 months and after 27 months. That's interesting. That is very interesting. So let's continue now. So the total sales, as I said before, is going to be rad 25 plus 2, which is 7. Now S of T is rad T plus 2, and F prime of T is 1 over 2 rad T. So when T equals 25, it's going to be, I'm going to plug in 25 up here, so I get 5 plus 2 is 7. For the derivative, I'm going to plug in 25 right here, and we're going to get 1 over 2 times 5, which is 1 over 10. So that's 1 over 10, which has a decimal is 0.1. 25 months from now, the total sales will be 7 million, and will be increasing at a rate of 0.1 million, 0.1 million, which is, by the way, $100,000 per month. Now, if this instantaneous rate of change of sales remain constant, the sales will grow to 7.1 million after 26 months and 7.2 million after 27 months. And this is, again, an estimation. If you want a more precise answer, you would have to actually plug 26 and 27 into the formula, which is a pain because it's a square root, which is because it's the square root of a number that's not a perfect square, so you get a bunch of decimals, but it's okay. Accuracy, I'm gonna say. So let's move on. I think we're okay. So let's talk about when things go wrong, because that happens too. Sometimes you're going to do the derivative and you're just going to find it doesn't work and it doesn't exist. And you're going to say, if that happens, it's non-differentiable. Now, it might be non-differentiable just at one point. It might be non-differentiable entirely. But if the derivative doesn't work out, it's not differentiable. And let's see. The last thing for this section, how can we just recognize by a graph if there's a derivative or not? So basically, at this point, when x equals a, where the function is not continuous, there will not be a derivative. Because derivative only works for a continuous function. This point has a sort of a sharp turn, because if I'm coming from this side, the slope is that way. If I'm coming from that side, the slope is that way. So if I have like a sharp corner, that's going to be no derivative. Now, this is going to be interesting because I'm going to wind up having a vertical tangent. When I come from this way, I get a vertical tangent. Come from that way, even though the left side and the right side agree, which is important, because here the left side and right side did not agree. Notice that left side agreeing with the right side, that came up with limits, that came up with continuous functions, and also comes up with derivatives, the idea of a left side equal right side. But here, even though the left side equals the right side, it's a vertical tangent. And here also is another vertical tangent. And here you have a vertical asymptote, but the function is not defined. So basically, in order for a function to be differentiable, it has to be continuous and what we call smooth. See, this guy here is not smooth because it has a sharp corner. So it has to be smooth and continuous. That's basically what we're saying here. And that's it for now. That's the end of this video. We'll see you guys next time. It's been loads of fun. I have herbology now. So I got to get going. It's been a lot of fun. Signing off from Hogwarts. Bye.